Zach Pulitzer from LinkedIn, Senior Staff Software Engineer.
All right, thank you. I congratulate you all for your impeccable taste, saving the best for last. Thanks for coming. My name is Zach, and I'm going to talk to you today about Venice's active-active replication architecture. By the end of this talk, I hope to convince you all that when the last writer only wins, we all lose. Actually, I've misplaced my clicker. Oh, there it is. Okay. A little about myself. I'm an engineer at LinkedIn, where I work on Venice. For the last 9 years, I've been working on database systems at LinkedIn, having joined the Venice team about 4 years ago. I spent most of my career working on distributed databases at different companies, and plenty of time agonizing about replication. We're going to break this talk up into 4 main parts. For the first half, we'll go over what Venice is and what problems it solves. We'll take this time to lay context for what motivated us to seek out an active-active architecture for our system, moving into what that looks like. We'll then get to the main thesis of today's presentation, where we'll explore why, in some cases, the last writer isn't always right, and then we'll conclude with what Venice does to remediate this problem for its users. So first and foremost, what is Venice? Venice is a database that specializes in hosting derived data. What is derived data exactly? Well, we define derived data to mean data which has been processed, formatted, inferred, maybe tossed around a little, from other data sources. Some examples of this would be the output of batch processing jobs, stream processing jobs, or AI model training. In fact, at LinkedIn, our AI engineers get a lot of leverage out of Venice. As an example, a team may run a model training job once a day or multiple times a day, and this training will output a large data set. Venice is able to consume that data set and make it available for querying from online applications at low latency. To explore the topic of derived data a bit more concretely here, we can see examples of primary data versus derived data at LinkedIn. A member profile is an example of primary data. It's data which is generated from a primary source. In the case here, our primary data source is you. That's right, you. Proud LinkedIn members, hopefully. And the data direct from this source would be your profile. As you add things to your profile and interact with the site, and as other members in your network provide updates and interact with the site, we stream those updates into our Hadoop grid. From there, we'll train models and compute input features, and at least once a day, sometimes more, we'll build our derived data set. In the case shown on the slide here, that derived data set is powering a LinkedIn feature called People You May Know, which is a feature that drives LinkedIn growth and member engagement. Today, at over 2,000 production stores, Venice powers many products at LinkedIn, along with People You May Know, like term and title standardization, search verticals, and even some security edge services. We target a P99 SLA of single-digit millisecond for single key lookups, and for some instantiations of Venice which leverage low latency clients, we are targeting a P99 that is sub-millisecond. We also proudly open source Venice almost exactly 1 year prior from today, live at Strangeloop, and have been building a community of users and contributors ever since. Moving past the product pitch and towards how users interact with Venice, we describe user interaction with Venice as if you were using a queue value store. We use this to separate Venice from the notion that it's a key value store, as a key value store implies synchronous interaction when applying writes. For users of Venice, this isn't the case. Writes apply to Venice asynchronously by being submitted to a queue. This is what enables us to do high throughput on data ingestion, as well as guarantee low read latency. We're able to do more by doing less in the online path. So let's first discuss the write path of Venice. Venice enables multiple inputs to be coalesced into a single store. There can be full version pushes which rewrite the data set at regular or irregular intervals, or records can be pulled in row by row. This diagram shows how Venice full push is orchestrated. When a full push occurs, our Venice push job, otherwise abbreviated to VPJ, transmits to Venice that a new version is being published. The Hadoop push job will sort and conditionally compress the data and assign it to Venice partitions, where it is then produced and consumed by Venice servers. Once all data has successfully been transmitted, Venice then swaps online traffic to the new version. The previous version then becomes a backup version, which is eventually purged out, but is kept for some period in the event that there's some data quality issue for the new version we need to swap back. This enables users to act with agility when they need to bulk load or reprocess their data sets without impacting live traffic. Incremental pushes from bulk data sources are also available and can be merged on top of version pushes. We allow for concurrent incremental pushes to be ongoing, which are then applied on top of all active versions that Venice is maintaining at a given time. This is to give flexibility for a potential rollback so that, should it be needed, the data is not stale, and to make sure that new data pushes are as fresh as desired with recent updates, which may not have been applied at time prior to doing the most recent version push. HDFS isn't the only input we allow. We also, in the same path, provide nearline updates from streaming sources like Kafka via Samza or from databases which have change capture support. These can be pulled in either incrementally or built into the same version push pipeline that HDFS paths leverage. And because users are forever impossible to satisfy, we also now support a standalone Venice producer, which can allow applications to produce writes to Venice in an async manner, similar in behavior to what you might expect from a producer client like Kafka's. Reading from Venice is a bit more straightforward. Listed here are Venice's 3 main read APIs, along with numbers on the peak traffic each API serves under LinkedIn site traffic. The first and simplest is single key gets. Just give a key, get a value. Simple and low latency. If you care more about throughput, then we also offer a batch get option. Give many keys, give as many values back. The last category we call read compute. Read compute is a bit more complicated, and I have here a short explanation on kind of what this is. The philosophy behind read compute is based on the observation that Venice is storage bound at LinkedIn, which means we usually have CPU to spare. So at the cost of some CPU, we can save on latency and network log by doing more computation on the server, as opposed to transmitting larger results that get computed in app nodes. To this end, we support projection of fields, basically select fields in a record instead of reading the whole thing, and matrix operations, which can be done on large matrices server-side, allowing us to have to only transmit a much smaller result to applications. And then further from those APIs, we have different ways that Venice can be used to materialize data. One way is via a client called DaVinci. DaVinci enables Venice users to load their Venice store either into their application memory or to local disk. Data is then kept fresh with the Venice store by applying the same follower write path to the application state that Venice follower replicas adhere to, giving the local cached view very low staleness. Venice also supports the ability to ETL data out of it, as well as subscribe to change capture events like you might be used to with other databases. So what motivated us to move towards an active-active architecture? To understand that, we need to look at what the architecture of Venice used to look like. Here we see this is the stuff that Venice is made of. This diagram represents what Venice internally looks like within a single data center. The upper services represent the client libraries and services involved in the Venice online read path, and the lower rectangle here represents the Venice cluster control plane. For today's talk, we'll be focusing on these middle pieces here, as they are most chiefly involved with the data transmission layer of Venice. Getting a closer look at those middle components on the previous slide, here we're looking at how that data sent from batch and streaming processes arrives in different data centers in the old architecture. In this diagram, we've assigned a color to each data center one of these services resides in. Writers from all or any data center must first publish data into DC0, where the data written there is replicated by Kafka MirrorMaker to the other production data centers, which is then ingested by Venice for serving. This architecture, however, had some shortcomings. First, this isn't truly active-active. It's active-passive with no failover. If DC0 is down, the entire write path is down. It's a single point of failure. Secondly, if you are a writer in, let's say, DC1, in order for your write to arrive in DC1, it must first go to DC0 and then come back to DC1, which means the latency for that write arriving is 2 data center hops. Moreover, Kafka MirrorMaker is a considerable operational burden for the number of topics created and destroyed by Venice, besides being an additional service which we have to maintain. We can actually address all 3 of these problems with a single solution: active-active writes. If all writes didn't have to travel always to a single data center prior to getting committed to Venice, we can eliminate the single point of failure of the platform, as well as gain a major efficiency bonus in both system performance as well as operational overhead. So now we'll look at how we were able to ditch the active-passive write model from the old architecture. Recalling the slide from earlier, we have 2 goals here. We need to have individual writers have the ability to transmit to any data center they may reside in directly, and we need to be able to extricate Kafka MirrorMaker from the architecture. With these goals in mind, it's not tenable to have this marshalling data center with KMM really in the mix here. So we remove DC0 entirely and introduce a new concept called the Venice leader-follower state model. In this model, instead of KMM hosts pushing data to different data centers to be consumed locally, we have Venice leader servers actively pulling data across data centers and publishing it to follower nodes, in much the same way that KMM was pulling data to be consumed by Venice. These leaders actively pull data from all of the data centers in a full replication mesh. Each writer publishing data is able to have its data pulled in directly with no cross data center hop, and then remote data centers get the data with a single hop, as opposed to 2 from the old setup. One challenge, however, is that now that we've removed active-passive from the architecture, we now need to be able to handle conflicting writes. Conflict resolution is more or less a necessary component to any replicating system which handles writes on multiple replicas. Our strategy for resolving those writes initially is fairly standard, and we have an example here where 2 writes in 2 data centers attempt to write to the same key but try to apply different values. As you can see, a writer in DC1 is attempting to update key X at timestamp 1, while at nearly the same time but a little later, another writer attempts to update the same key from another data center to a different value at TS2. For a brief period, data may diverge. The local writes apply in both data centers, and for a time there is an inconsistent view. We can see both writers have applied their updates to the data centers they were writing to. The divergence is short-lived, however. The write which came from DC1 at TS1 replicated to DC2, but was ignored as it had a time value which was less than what had already been persisted. In DC1, the write from DC2 applied as it was from a time which was greater than what was previously persisted. At this time, data is now consistent. This is a last writer wins model that is common between systems that many of us are probably familiar with. So maybe the last writer winning isn't so bad. It might not be that bad, except now we have a new problem. Recall that Venice is all about ingesting from different sources. How do we empower users to push data from these different sources without having to fret about stepping on each other's toes? So let's get to the core thesis of this talk, and it's the problem of the last writer winning. What do we lose when the last writer wins? The last writer winning as a strategy leads to a famous problem known as the lost update problem. This is a concurrency problem in databases. At a high level, the lost update problem occurs when 2 competing writers try to update the same record in a database. The effect is that only one of these writes will actually get committed, or win, and as a result, the other update is lost. Let's demonstrate it with a traditional online database interaction. We have Alice here who is updating a record in a database. At roughly the same time, but just a bit later, Bob also updates the same record, but with a different value. The result of this interaction is that only Bob's update was persisted. Alice is left wondering what the heck happened here, and Bob, I suppose, goes about the rest of his day as if nothing happened. This isn't a very new problem and has, in fact, probably existed for as long as databases have. We have a few common ways of dealing with this, so let's look at one of them. Let's go through that scenario again, but this time we're going to use a strategy that is pretty common called optimistic locking. Again, we'll have Alice transmit their update to the database. Bob will begin their write as well, but Bob will supply instructions to the database that their write should only apply to the database conditionally. Bob is using something called a conditional header. There are a handful of conditional header options that you may have seen elsewhere, things like etag match, if modified, etc. Here, Bob is telling the database to apply their write if the record hasn't been modified recently. When this happens, Bob's write will fail and they will receive an error. Bob will then decide what to do next, potentially reading back the data which was committed and deciding how to merge the update with what's currently in the database, or giving up the write entirely, and really it depends on what Bob wants to happen. This is a very common scenario when interacting with a data system where operations are performed peer-to-peer in a synchronous manner. Now that approach worked great for Alice and Bob because they were interacting with the same database directly, which gave read after write consistency. However, a lot of data systems, especially data systems which need to replicate between data centers, make use of asynchronous replication. Bringing Alice and Bob back, this time Alice is talking to a database replica which is local to them, perhaps in a data center that is nearby their location. Bob then at roughly the same time performs a write to another replica of this database that is local to them, but one that is different from the one Alice just updated. Then things replicate. In this example, this database is using a last writer wins conflict resolution, similar to the one that we described earlier. Alice's update will try to replicate to the other data center, but will get dropped. Meanwhile, Bob's update will replicate and be accepted. The data is consistent, so the database did exactly what it was designed to do. It became eventually consistent. But even though Bob used optimistic locking when applying their write, they still managed to clobber Alice's update. Alice quits the next day. So now that we've talked about the lost update problem and how it usually affects databases, you might have noticed something. The real crux of the issue is that Alice and Bob either weren't or couldn't coordinate in a synchronous manner. The lost update problem is really a problem of asynchronous systems. And given that we find ourselves in attendance at a streaming conference, that can only mean that, that's right, this problem isn't specific to just online database communication, but is also problematic for stream processors as well. Let's say you have a stream processing job which is made up of processors which are members of a consumer group doing work on some input topic. Partitions of this stream topic are load balanced between instances, and they process events and commit them to a database. Now let's say that we have two events written to this topic, and we might expect some logical ordering. We have event 1 and event 2, and both happen to go to two different partitions on the stream topic. Now, one processor slows down for some reason. Maybe it's garbage collection, maybe it's a disk or hardware failure, but the effect of this is that one processor gets further along on the input topic than its fellow. It consumed event 2 and writes it to the database. The other processor then recovers from its malaise and processes the earlier event from the input topic and writes it to the database. Now we have a situation where the last writer didn't even have the latest data. The earlier data is now committed to the database, and we've lost the newer data, it having been overwritten. So now that we've explored the problem, let's look at how we solve this for Venice users. We address this with a family of operations that we call write compute in Venice. Recall how we highlighted earlier that concurrent updates are hard. The cases we've talked about so far have all leveraged row-based protocols for writing and replicating data. In a model where we have to publish full records to replicas, there isn't a scenario where we either have our writer lose data or be on the hook to store all conflicts to be resolved later by the reading application. This is a strategy sometimes known as read repair. So from the previous examples, writers were writing entire records. However, without a locking scheme, optimistic or otherwise, there can arise an issue of correctness. Operation-based replication is a popular approach, and it can certainly help. If we could merge instead of clobbering conflicts, we can improve things, but we need to be careful. Recall, Venice is hosting upwards of 2,000 different stores and use cases. If you're familiar with something like Oracle Golden Gate, then you know you can set up replicators to perform business logic to remedy conflicts, but it's not something we can support trivially at the size we're running. We would struggle to support plugging merge logic across so many use cases, all the while trying to guarantee high write throughput. So what we need is something which gets us to the merge benefit, but perhaps it's a more constrained set of operations than arbitrary stored procedure logic. CRDTs are a happy medium and our answer. CRDTs have gotten a lot of attention over the last 10 years in the database world and have a lot of interesting uses. We can use CRDTs to articulate Venice write operations and transmit them to replicas in different data centers. We call this family of operations in Venice write compute. Let's see what Venice write compute looks like. We'll start out with a record which contains fields A and B set to 5 and foo, respectively. Here we have two writers writing to the same key X. However, instead of writing a full record which contains A and B, each writer will only write to the fields they care to update. In this case, we have one processor updating field A in record X, and another concurrent processor writing to key X in field B. Both of these writes will apply and merge and result in a brand new record where no one lost their update. So that looks good for within a data center, but what about two data centers? Well, in the example database we had with Bob and Alice earlier, there was a dichotomy in how writes were handled. Users of the database had synchronous interaction, while replication was asynchronous. This divergence was perhaps somewhat to blame for some of the difficulty in handling merging. In Venice, however, there is no dichotomy. It's all handled the same. Let's see how that plays out and how it's architected. Here we have two processors in as many data centers writing concurrently to Venice. Here we have them applying partial updates as opposed to full records. Write compute updates, write compute partial updates. DC1 is updating fields A and C for key X, while DC2 processor is updating fields B and C. For a time again, data diverges between data centers as the individual fields are updated and applied to the local data center. Here we see the writer in DC1 has applied updates to fields A and C, while the second writer applies to fields B and C. And then things replicate. The updates to fields B and C travel from DC2 to DC1 and are applied, while keeping the previous update to field A. The updates are merged, resulting in a brand new row that merges the output from the concurrent processors. Similarly, we come to the same result in DC2. After the write from DC1 replicates, we keep the update to field A, but drop the updates from B and C. In this way, we've managed to merge the results from the two processors, and neither processor has the entirety of the data they transmitted dropped, which is a fundamental improvement on losing the whole update. And since this is current, it'd be amiss to leave the slow stream processor out in the cold. We can also rely on write compute to help us out. We do that by enabling users to define the causality of their input. Recall the scenario I highlighted earlier with the stream processors. You might notice that even with what we've talked about so far, if the one stream processor slows down for any reason, we'll still wind up with old data. Looking at the input data, if each processor processes one of these messages, it's still not hard to imagine the scenario where we clobber the later update and lose data on field C. Except this time, while using Venice, we're going to specify a bit more information with the update. The processor will actually transmit to Venice a timestamp which isn't based in the current time, but rather is based on a logical time from the input source. Technically speaking, this need not be a timestamp. It only needs to be some number which enables causal ordering of events relative to each other on an input, like a stream offset or a database transaction ID. We enable Venice users to specify this value at time of producing data to Venice. Now when the processor wakes up, it will transmit its update with t equals 1. This will result in a merge where we keep fields A and C from the older update with newer data and merge in the update which contained field B, but dropping C as its older data. Now the last writer doesn't win, rather it compromises. So why is this powerful? Well, it allows us to enable use cases where processors no longer have to care about each other in a single data center or multiple ones. In the example database we highlighted earlier, applications would have to programmatically handle optimistic concurrency strategies. However, those strategies are not complete solutions and are completely compounded by row-based eventually consistent replication. There's no difference logic-wise between a local write and a remote one in Venice. Both are subject to the same resolution, simplifying user experience. We've talked a lot today about full record updates and partial record updates, but in addition to those, we do support the ability to do collection operations on sets, lists, and maps. These are all the write compute operations we today support. And all operations have support for user-specified timestamps. Taking it all in, we were able to resolve all the issues from the previous architecture, reducing costs and improving the overall quality of life of Venice users. No more extra transmissions cross data center, no more linchpin data center, no more mirror maker, and we've added functionality for our engineers to leverage. To call out some more concrete ones, in addition to pushing the envelope for ease of use of the infrastructure, this architecture actually enables us to bring in a lot of new use cases within LinkedIn, examples being ads and title standardization, and some of these folks which have more complicated upstream processing that need to sync into the database. We're also able to decommission 500 Kafka mirror maker instances via this new architecture and reduce the cross-fabric data transmission by half. Now, one last topic, if you'll indulge me. We made this new architecture for Venice, and we gave a guarantee of eventual consistency, but how are we monitoring that? It turns out, even with a solid design, things can happen. In Venice, servers bootstrap out of Kafka, and Kafka is how we're transmitting client operations. Any imaginable outage of Kafka is one where data integrity might be at risk. And then beyond Kafka, we could have errors in new versions of the software. Recall, Venice servers in different data centers are all consuming write compute events individually and transmitting to local replicas. This implies that leaders in different data centers at potentially different software versions need to come to the same conclusion deterministically. This itself isn't insurmountable, but it doesn't hurt to keep an eye on it. We do that by doing data consistency validation in Venice with an algorithm we developed called Leapfrog. Leapfrog is an algorithm that can generically be applied to any database where it's possible to consume that database's changelog for two replicas that you're trying to compare. It does so by consuming the changelog of these two replicas and making determinations on the result of those changelogs to see if they diverge. The algorithm works in two stages. The first is to determine starting points in changelogs of the two replicas. It could be at the beginning or it could be at the tail of the last compaction. It really depends case by case. The next step is to look at records either from a compacted view of the data set or row by row on the changelog. Which you choose depends where you are trying to run Leapfrog, either in batch settings like on HDFS or in stream processing. It then comes to one of three conclusions. The data set is either consistent, all data is replicated, no inconsistencies. The data is not consistent yet, which will be the case for some amount of data at the tail for eventually consistent systems, or the data has diverged. Then the process repeats. Let's watch this in action. Here I have the changelog for one replica. Each event in the changelog has a key, a value, and a vector of offsets that we've labeled TS. This vector is meant to represent event IDs, which correlate to upstream events transmitted by the different sites. Since we're comparing two sites, our vector has two components. To dissect one of these, the first event in this changelog represents a row keyed by bar with a value of fox, and a TS that says this key was altered at offset 0 from one site and offset 100 from another site. Now we introduce our second replica on another site. We can see that at the head of our topic, the second site has slightly different values for some keys. We then get the high watermark over a section of the changelog of each replica we're comparing. The high watermark is defined as a vector which contains the highest offsets of the updates we've heretofore seen from different sites. Looking at these two replicas, we can see that topic B has a high watermark with a component vector which is larger than topic A, but lower for another. This tells us that topic B has some events from one site that topic A does not have, but also is short some events from another site. In order to make our comparison, we need to have one of these replicas completely ahead of the other. We're going to select one of these replicas and have it leap over the other. Our leap should make sure that all component vectors of the high watermark have progressed beyond the other replica we're seeking to compare. So now let's compare our keys. Our first key is bar. Both replicas have the same value for the key. They're consistent, no problem here. Now let's look at key foo. In topic A, key foo is set to value horse, and in topic B, it's set to mule. Initially, the key in topic B was based on a state where the high watermark that was not completely ahead of the other replica. So we move ahead. We see that it now has value burro. Since the key values are not the same, they're not consistent, but that doesn't necessarily mean they diverge. The record timestamp vector indicates that the value in topic B was updated by some message which is beyond the high watermark of topic A. This indicates that while the records aren't consistent, they might be consistent later. So we don't flag these rows for now. Now we get to key fizz where something interesting happens. Key fizz has differing values. Looking at the record in topic A, its record TS vector falls below the high watermark of topic B. This means that the replica represented by topic B has seen all events that are pertinent to the final row result of the record in topic A. The same is true vice versa. The replica represented by topic B has a high watermark that supersedes the TS vector in topic A. So what does that mean? What does this mean? It's an inconsistency. The methodology of this algorithm asserts that both replicas have enough information to come to the same conclusion, but did not for some reason. Maybe it was missing events, maybe it was an inconsistency in how the data was computed, maybe Mercury was in retrograde. Interesting, but that's for whoever's debugging the issue to figure out. In our case, the leapfrog algorithm has done its job and flagged the error. And then finally, to finish out the algorithm steps, just to check on that last key, after doing our comparison, we now choose topic A to be our leap our leap data center, and have it jump forward in time so that it now has a high watermark that is greater than topic B. We now see that that key foo did become eventually consistent between the two replicas, and the whole thing repeats itself so long as we have more data to compare. Leapfrog is an algorithm we can run in batch or streaming environments. At LinkedIn today, we run it in batch mode with some proprietary pieces, but we're in the works to expand it to work with open source Beam completely. The first iteration was made to work per partition for a store, but with an augmentation to the algorithm we call Lilypad, which selects all interesting leap points in the stream, it can actually scale to an arbitrary number of MR workers with a theoretical upper limit of the number of keys in the dataset. We used Leapfrog in our nascent testing of our architecture and found edge cases before they could get to production. Additionally, we have also written a functional specification of the algorithm using TLA+. And TLA+ model checker has been an invaluable tool in doing rigorous checking of the model. We hope to write a paper on this topic. And now we are drawing to the conclusion of this talk. We have a long road ahead of us in Venice, and there's really all kinds of things we're looking to include. Some examples as we go, we hope to expand the family of write compute operations beyond partial update with CRDT arithmetic operations, something akin to a materialized aggregate or even just simple counters. We also would like to completely open source our data validator and its components. Right now, only some parts of it are available, like the TLA+ spec, and some test cases to show its behavior. We're also eager to see the flexibility of our design by seeing what other pub implementations out there can be run on Venice. Right now, it's very much Kafka. And then most important of all, your contributions. We open sourced Venice with the intent of building a developer community around it, so do please come check it out. I filed a backlog of good first-time contributor items for anyone curious this week, so please take a look. We're eager for external contributions. And finally, concluding on a shameless plug, if any of you happen to be attending KubeCon next week in San Francisco, my colleague Gao Jie will also be presenting on Venice. He will be focusing on how we optimize Venice to be able to handle over 1 million operations per second per server. He'll be co-presenting with Alex Dubrowski, who works on Java performance at LinkedIn, and he'll be sharing how we tune the JVM to reach this performance milestone.